CCI, Crash Course Instrumentation, presents Episode 69. Series Parallel Basics. What makes a circuit series parallel? Standing credit. Thank you to Tony R. Coupault and the open source community for the Mod L project. Opening hook. Why do two lamps sometimes get dimmer when you add a third, yet the battery has to deliver more current at the very same time? Today we decode that puzzle using series and parallel thinking, with no bench gear required. Roadmap. First, plain English definitions. Then, how to spot series and parallel anywhere. Next, a 5-step mental playbook you can run in your head. Finally, a short historical note on current arrows. Plain English definitions that stick. Series means a single path for current, like a one-lane road where every car passes the same checkpoints in the same order. Parallel means components share the same two connection points, like two doors in the same wall. Whichever you choose, you start and end in the same rooms. Memory aid. Series shares current. Parallel shares voltage. What makes a circuit series parallel? Real circuits mix both. A parallel cluster may sit in series with something else or vice versa. If two parts connect only to each other at a junction with no other branch, they're in series. If two parts tie to the same pair of nodes, they're in parallel. The mental playbook. Annotate. Mark what's shared. Same current along series strings. Same voltage across parallel sets. Reduce. Replace the recognized group with a simpler equivalent. Series resistances add. Parallel resistances combine to something smaller than either member. Solve. Once reduced to a single equivalent at the source terminals, use Ohm's law in words. Voltage equals current times resistance. Expand. Unfold one step at a time. In series, copy the current through each member. In parallel, copy the voltage across each member. Fill missing values with Ohm's law. Check. Loop sums, voltage rises and drops, must equal 0. Node sums, currents in and out, must balance. How to see series and parallel without drawings. Picture 3 resistors named left, middle, right. If middle touches only left and right and nothing else branches at that junction, the 3 are in series. One current for all. Picture 2 resistors both tied between the top rail and the bottom rail. Because their ends share the same rails, they're parallel. Same voltage on both. Current splits according to resistance. If a spec says, the sensor and the indicator share 2 terminals, think parallel. If it says fuse, then switch feeding one device, think series. Common traps and how to dodge them. Hidden branch. A thin wire peeling off a series junction makes it a node, no longer pure series. Breadboard gaps. Some rows are split. Don't assume the whole strip is one node. Intuition flip. Adding a parallel path. Lowers. Total resistance. Source current goes up. Adding a series element. Raises. Total resistance. Source current goes down. Voltage behavior follows the rule. Parallel shares voltage. Series divides it. Thought experiments you can run in your head. 2 equal resistors in series share the same current. Each drops half the source voltage. 2 equal resistors in parallel. Each see the full source voltage. The total current splits equally. 2 in parallel, with that block in series, with a third. First imagine the parallel pair as an easier single path, smaller resistance. The one source current flows through the lone series resistor, then splits inside the pair and rejoins afterward. Why this matters to technicians: measurements change circuits. A voltmeter sits in parallel with what it probes and can change divider ratios. An ammeter sits in series and adds a small resistance. Thinking series parallel lets you predict the direction of change before you connect. Fault logic. An open in a series path kills everything downstream. An open in one parallel branch lowers total current, but other branches can keep working. That narrows troubleshooting fast. Panel work. Many real devices are simple dividers feeding loads. Treat each addition as either a series gate or a parallel tap and reason from there. Short historical note. We draw current from positive to negative because early scientists defined conventional current before electrons were discovered. Even after learning that electrons drift the other way in metals, engineering kept the convention so everyone speaks the same schematic language. Wrap and next steps. Remember, series shares current, parallel shares voltage. Annotate, reduce, solve, expand, check. That habit solves every combination circuit you'll meet, thanks to Tony R. Kupalt and the open source community. Next up, episode 70, running the full playbook in words only.